So now we're going to add another idea to compound interest called annuities. And what you're doing with an annuity is you're going to be applying a compound interest, but in addition to that, you're going to be making sequential payments or deposits into the account as well. So not only do you have your initial principal and the interest earned on it, but you're also going to be adding in more deposits at regular time intervals and adding interest to those. Okay, so an annuity, that's what an annuity is. An annuity is a sequence of equal payments made at equal time periods that earns interest. Okay, so you make a deposit, you're earning interest on it, and then at a certain time period, maybe it's every year or maybe it's every month, you make another deposit, and then you earn interest on all of that accrued value, and then at the end of the next time period you make another deposit, and then you're still earning interest on all of that. Okay, so it's deposit, interest, deposit, more interest, deposit, more interest, or payment, I guess, instead of deposit, but either way. And so an annuity can be derived, the formula can be derived. I won't go through all the details, but I'll just give it a motivation here. We know the annual compound interest formula is A equals P times 1 plus R over to the T, okay? That's the formula that we've seen in the compound interest section. It's when the N value for the compounding interest formula was equal to 1. And so, right, annual, 1 time per year. And so if we just assume for a minute that you're making payments every year, so you make a payment at the end of the first year, or at the beginning of the first year you make a payment, at the end of that year you earn interest, and then make another payment at the beginning of the second year, and at the end of the second year you get interest, and then make another payment, and so forth. And so as this happens, the amount in the account or in the annuity is calculated using the following formula. I'll kind of break this down 1 year at a time. So the annuity here, the amount is A, and we'll call it A1 because this will be the amount after the first year. So that you make a payment beginning of the first year, at the end of it, that's what you have in there. Then you earn interest. Okay, so we're going to say that the original principal is, or the payment, we'll use P for payment instead of principal this time, I guess. The original payment is what you have after the end of the first year. Then going into the second year, you take that payment, you earn the interest from the first year, which is applying the 1 plus R interest rate, and then you add to that another payment. Now the payments are equal, right? Equal payments, equal time period. So every year, at least in this example, we're going to go every year, you input another payment of P. All right, then you let this ride for a year, and that should be A2. I'm sorry. Then at the end of the second year, or I'm sorry, at the end of the third year, then, because this is what's coming out of the second year, going into the third year. Sorry. Then, as you get to the end of the third year, you basically apply an interest rate to both of these terms because you've got to earn interest on everything that's already there. So it's going to be an extra factor on that first term. It's going to be another interest rate earned on the second payment. And then you have to add in another payment. Okay? And you continue this process, right? So at the end of the fourth year, you have interest earned again on that first year's payment, another set of interest earned on the second year's payment, then you've earned interest on the third year's payment, and then you have to make a payment for the fourth year, and so on, right? And so that's kind of the progression that you'll see. Now, a lot of times you'll see this flipped around so that the sequence kind of builds going the other direction. So let's say, I'm going to do that, we're going to say after T years, so the annuity after T years, I'll put a subscript of T there. that's going to be, and I'm going to start on the right side and work my way to the left. It's P plus P times 1 plus R plus P times 1 plus R squared plus P times 1 plus R to the third plus, and you keep going with that pattern until you hit the teeth year. But notice, I don't want to stop at P times 1 plus R to the T, that'd be too far. Notice that the largest power is always 1 less than the year. Okay, so here's power 1, 2, and so forth. So it's actually 1 less, so I want T minus 1 up there in the exponent. So if I went 20 years, I'd want this last power to be 19. Okay, because the interest is always applied at the end of the year, not at the beginning. You have to earn that interest over the course of the year. That money has to ride in the account, in the annuity, for that full year before you earn the interest. Okay, now that's the amount after T years. Okay, now you can actually make this formula look nicer. This formula here is called a geometric series. The geometric series has some very neat formulas and properties associated with it that we don't cover in this course, but I'm going to kind of wave my hands and say, abracadabra, here's a formula that will work. It's basically a shortcut to calculating all these long terms, okay? And the shortcut for that is the final amount after T years is a fraction P, oops, actually I want that to be a bracket, don't I? P times bracket parenthesis 1 plus R to the T all minus 1. That actually looks like the effective yield, which it kind of is, the effective yield. Oh no, the effective yield didn't have the T value up there. So it's the effective yield, but with the T instead. And then the R in the denominator. There it is. The rate in the, so you divide out the rate. Again, the formula for this comes from the fact that we have a geometric series here, which is the sum of a certain number of terms, where each term is found by multiplying the previous term by an extra factor of something. Okay, and so the formula for the sum of that kind of sequential pattern is found using this formula. It turns out to be that formula. Okay, now what does that mean? Well, I'm going to get rid of all this craziness here. And we're going to stick with this formula now. So let's give a hard example. Let's say you wanted to invest, in an IRA. An IRA is a type of retirement fund or retirement savings, and you can invest, I believe it's up to $6,000 per year into an IRA, and you earn some interest on it. Now let me just give you an example. Let's say we were putting in a payment of $6,000. We'll just use that as an example. You were maxing out your IRA every year. You put in your $6,000, and let's say, and I don't know what a reasonable interest rate is, I'm just going to go with, I don't know, maybe a 3% interest rate. I'm sure that's low, and it does vary over time, but I'm going to go with that for now. And then let's say that you wanted to do this repeated pattern for a period of, let's say, 20 years. Okay, so maybe you're 45 years old and you want to do this till you're 65. You could adjust all these values as needed. And so what I want to do is figure out what the annuity is, what the value of that investment is at the end of the 20 years, right? So you're depositing $600 or $6,000 every year, and then you're earning interest on all that previous amount every year. And so to find that value, we calculate the $6,000 times this quantity, which is 1 plus 0.03 raised to the 20th power minus 1, and then all divided by 0.03. Okay, so I've put in my principal, my payment, that periodic deposit. The 3% interest is located in two different places, and the 20-year period is our exponent. And so then we have to punch that into our calculator. You get 6,000 times, now I'm going to use a couple sets of parentheses, 1 plus 0.03 raised to the 20th power minus 1 parenthesis. Now, maybe I'll even write this out rather than trying to show you the calculator, because it's not fitting in one line. So if I'm typing this in the calculator, I'm typing in 6,000 parenthesis 1 plus 0.03 parenthesis raised to the 20th minus 1 parenthesis divided by 0.03. And that gives me a nice chunk of change at the end of the 20 years. $161,222.25 if I round to the nearest penny. All right, so that's a decent amount right there. Now, not all of that difference is interest, right? You're earning that not on $6,000, but $6,000 applied every year for 20 years. Well, if you think about what that amounts to, how much did you actually invest versus how much of interest did you get back? So the interest itself, if you wanted to calculate that, is equal to that final annuity value, minus the payment times the number of payments. So it'd be 6,000 times 20, right? 20 payments of $6,000 that you invested. Take that off of this annuity value, and that gives you how much interest you actually earned. So 60,000 times 20 is what? 120,000? Or 6,000, I'm sorry. 6,000 times 20 is, 120,000. So you would have to take $161,225.25 and subtract off 120,000, and you would get $41,225.25. So if you're doing that every year for 20 years at a 3% interest rate, you will have earned $41,225.25 in interest on that total amount that you've been investing. Okay, so it's kind of a neat formula. It's fairly, it's simple in its theory, but it's complicated just to get it typed into the calculator is not an easy thing to do. But if you're careful and you get the parentheses in the right spots, that can be done nicely, and that can give you a pretty good calculation. Now, there's variations to this because a lot of your annuities are not, you're not making payments every year. Some of them you'll be making payments monthly. And so this might even be more applicable as you're looking at, say, credit card payments or payments on a mortgage loan or something where you make payments on a monthly basis. This might be more applicable, but we can do this with all sorts of annuities as well. So in general then, if you're compounding, so this is an annuity that compounds yearly or make payments yearly. So I'll call this annual payment. Now if we wanted N payments per year, so you're making, instead of, maybe it's monthly, maybe it's daily, I don't know, probably monthly is the most common. you basically make the same adjustments to this formula as we did with the compound interest. Anywhere the R shows up, you divide it by N, so you have 1/n of the rate at each compounding period. So it's P times 1 plus R over N. And anywhere there's a T, you have to multiply it by the N, because you're not looking for every T years. You're looking actually to calculate this at every payment period, which is N times T total. NT, then you have your minus 1, and then you divide the whole thing. Now the R again gets, the R gets divided by N again. So it's R over N, so you get a fraction inside of a fraction there, which isn't too difficult to deal with. We're just plugging numbers in here, so just using the order of operations or our calculator to do that. So if I were to take, let's say, the same situation we just looked at, but let's, well, that seems unreasonable to put $6,000 in every month. It's going to be monthly. Let's do a different payment. Let's just change it up a little bit. Let's say you were making, I don't know, you were putting in $50 per month. So payments of $50 per month at an interest rate of 4.5%, and you want it to compound, or no, payments are going to be made, it's every month, I already said that, so N is 12, and you're going to have a T value of, let's say, 15 years. Okay, so let's just go with this information. We'll just calculate this straightforward. So the annuity value is going to be 50 times 1 plus, the R is 4.5%, so 0.045, over the N value, so it's monthly, that's an N value of 12, raised to the NT, so 12 times 15 power. Then you subtract the 1 and divide that whole thing by R over N again, which is 0.045 over 12. Okay, so all of that can go into my calculator. When I punch it in the calculator, it's going to look like 50 parenthesis 1 plus 0.045 over 12 parenthesis. I'll punch in the 12 times 15. Now some of you will have calculators that actually pop that up into the superscript, in which case you can just punch 12 times 15 in. Some of you will have calculators instead that put a little caret in there, in which case you want to surround that 12 times 15 by a set of parentheses. So it just depends on really the age of your calculator. So that's my exponent. Then we subtract off the 1. Oh, I don't want a bracket. I'm going to go parenthesis on the calculator there. So again, this is how I would type it into the calculator. Then I go divide by parentheses 0.045 over 12. Right, so this line right here is how I would punch it into the calculator. I think that will be pretty effective. 1 plus 0.045 over 12. Raise that to the 12 times 15 power minus 1 parenthesis divide by parenthesis 0.045 times, divided by 12. It's quite a bit to get typed in there. And final value is going to be $12,820.73. So that's the final value in the annuity at the end of that 15-year period. Now, if you're just looking to figure out how much interest you earned versus how much you contributed to that annuity, the interest, just like we calculated before, or similar to what we calculated before. Interest is going to be that final value minus the payment times the number of payments, but the number of payments is actually NT, right? It's the combination of N times T, not just T and not just N. You need the number of payments per year times the number of years, so it's the whole 12 times 15 right there. And so that value would be 12,820.73 cents, and then you're going to subtract off PNT, which is 50 times 12 times 15, which is $9,000 on the dot. You subtract that off and you get $3,820.73. So you definitely have over a quarter of the value of that annuity as an interest, okay, over the course of that 15-year period. So making some pretty good interest there. Even on a 4.5% interest rate, you still have over a quarter of the investment as interest at the end. Okay, so that's kind of a neat calculation. You've got really these two variations. Again, on a test, just like with compound interest, I'll give you these formulas. Your job is to plug stuff in appropriately. There is one other topic related to these, and that is if you wanted to, kind of rearranging the variables here, if you wanted to find the payment needed to achieve a certain amount at the end of a time period, you could actually solve these equations for P and calculate the value for A. I'm sorry, solve the equations for P and use the value for A to solve P, or to find a value for P. So how would we do that? Basically, let's just take this top equation. If you were to solve for P, notice that P is a multiplier. P is multiplying this whole fraction essentially. You could actually peel the P off and just look at it as P times a fraction. Well, how do you solve for P? You multiply by the reciprocal of that fraction on both sides of the equation. So that would tell you that P must equal A times R over that 1 plus R to the T minus 1. Okay, so that would be our formula for solving for the payment on an annual interest. Now, if it wasn't an annual interest, if it was something else, you have to take this fraction minus the P, multiply it by its reciprocal. So P in that case would equal A times R over N all over the quantity 1 plus R over N to the N T minus 1. It's almost redundant to even have that bracket in there because I've got that separated in the denominator, so maybe I won't even include the brackets. I'm not sure how your textbook actually writes that formula. They do include the brackets. I don't really think that's necessary. Either way, you can have the brackets or not there. You'd want them, I guess, if you're punching this in a calculator, you're going to want a set of parentheses or brackets down there. So maybe I'll leave them. But anyway, so you use these formulas and punch stuff in to find that value. So let's say, for instance, you wanted to have a final amount in your annuity of, let's say, $100,000. Let's see, you want A to be $100,000 at the end of, let's say, 30 years. T is 30 years, and you're making payments every month. So the question is, how big do your payments have to be? Okay, And so we can figure that out. We also need an interest rate. This is all moot if we don't have an interest rate. Let's say we know the interest rate to be 2.5%. That'll work. Something. So I want this bottom formula. I know the annuity. Let's go. That's going to be 100,000 times R over N, which is 0.025 over 12, all over that quantity right there. So 1 plus 0.025 over 12 again, raised to the NT. So we've got 30 times 12 is 360. Minus 1, that'll just make that calculation a little bit easier to finish that 360 off. And so put that in my calculator. I got 100,000 times, I'm just gonna, when I type this in, I'm gonna do the 100,000 times the numerator 0.025 over 12, and then I'm going to divide that by the other stuff, which all needs more parentheses. So there's a parenthesis to group the entire denominator, and then I need a parenthesis for the 1 plus 0.025 over 12 raised to the 360, and then the minus 1. So double parenthesis 1 plus 0.025 over 12 raised to the 360 minus 1, and then another parenthesis to close it off. And that tells me I need to deposit $186.79, rounding that wrong, 79 cents every month. Okay, so at a 2.5% interest rate for 30 years, if you deposited $186.79 every month over a 30-year period, you would accrue $100,000, including the interest. Okay, so that's kind of neat. Yeah, that's a decent amount, but it's somewhat reasonable. So anyway, those are kind of neat, some neat exercises. Both trying to determine the amount from the payment and trying to determine the payment from the amount. They both work out pretty well. Just have to determine which formula to use or which variation of the formula to use. Again, on the test, I give you the formulas. You just got to plug stuff in, maybe solve for a variable. But either way, you won't have to memorize those formulas for the test.